Welcome to our online chemistry class. Myself, KHARGE from SSPMS and Junior College, Shivajinagar, Pune 5. Our topic is electrochemistry. Let us discuss part number 6. Let us discuss reference electrode. What is a reference electrode? It is defined as an electrode whose potential is exactly known or is arbitrarily taken as 0. That electrode is called as a reference electrode. So there are two types of reference electrode. First one is primary reference electrode. Example is standard hydrogen electrode. It is also known as SHE. So here this primary reference electrode has potential is equal to 0. Okay, so it has a known potential, that's why it is known as primary reference electrode. While there are some another electrode, that is the second type, is known as secondary reference electrode, whose potential is determined by using this standard hydrogen electrode, and it is called as secondary reference electrode. Example is calomel electrode, silver chloride electrode, glass electrode. These are some examples. But in your syllabus, only primary reference electrode is included. So we will discuss only that. So let us discuss in detail standard hydrogen electrode SHE. So first of all, what is the meaning of this SHE? An electrode in which pure and dry hydrogen gas is bubbled at platinum plate coated with platinum black at 1 atmospheric pressure, placed in a solution containing 1 molar HCl solution or H plus ion solution, that is called as standard hydrogen electrode. Let us discuss the diagram. So here, with the help of this diagram, we will see the construction. Okay, the cell consists of thin glass tube in which platinum wire is sealed. There is a small amount of mercury at the bottom of the glass tube. So you can see here at the bottom the mercury is placed. Then the lower end of platinum wire is attached to platinized platinum plate coated with platinum black. Here, platinum foil coated with platinum black. Then the glass tube is covered with an outer glass jacket. This glass tube is covered with outer glass jacket. Then the glass jacket has an inlet at the top to pass the pure and dry hydrogen gas under 1 atmospheric pressure, which get dissolved in the solution to keep it saturated, and the whole assembly is then placed in a solution containing 1 molar H plus ion solution. So detail about this diagram and the construction of cell we will discuss. Now how to formulate the cell or how to represent the standard hydrogen electrode. The H plus 1 molar means concentration of electrolyte is 1 molar containing H plus ion. So for example we use HCl. Then hydrogen gas get passed at 1 atmospheric pressure into that 1 molar H plus ion solution, and here hydrogen gas is used and H plus ions are there, but there is no hydrogen in metallic form. So to make contact with another electrode, we have to use platinum wire. So that's why here platinum is used. It is a gas electrode. Okay. So for contact with another electrode, we have to use platinum wire. So this is the representation of this cell. Then we have to see the reaction, electrode reaction and EMF. So platinized platinum black capable of absorbing large quantity of pure and dry hydrogen gas. Okay, and this hydrogen gas changes to H plus ion and reverse process to occur. So let us see the reaction. We know that H carrying 1 plus charge, molarity is 1 molar. So H plus gain 1 electron to produce hydrogen, but hydrogen is unstable in atomic form. So one hydrogen combined with another hydrogen to form hydrogen molecule. So to prepare 2 hydrogen atom, that means 1 molecule of hydrogen, we require 2 H plus ion. So 2 H plus ion in 1 molar concentrated in its ionic form accept 2 electron and it gets converted to 2 hydrogen atom, that means 1 hydrogen molecule of that gas, and the pressure is 1 atm. So what is the EMF of this SHE? It is 0.00 volt. Okay, it is represented by EH2 because hydrogen gas is the gas electrode. Then we have to discuss the application part, application of SHE. So SHE is used as a primary reference electrode to determine the standard potential of another electrode. That's why it is called as primary reference electrode. Just now we observe that the EMF of this cell is 0.0 volt. So when we combine another electrode whose potential is to be determined, then that is combined with SHE. So to determine the standard potential of zinc electrode, it is combined with SHE. So let us see the diagram. So in this diagram, on right hand side the SHE is placed, and in left hand side of your cell zinc electrode is placed. So let us see the construction of these two half cells. So zinc electrode is placed in 1 molar zinc sulfate solution. In right hand cell the SHE is placed in 1 molar H plus ion solution. Then 2 half cells are connected through salt bridge, and these 2 electrodes are connected through a voltmeter by external wire. Then on left hand side zinc electrode is placed, so it acts as the anode. So zinc in solid state in presence of zinc 2 plus ion 1 molar solution or ZnSO4, and on right hand side there is a hydrogen electrode, that is standard hydrogen electrode. So platinum wire is in contact with hydrogen gas at 1 atmosphere pressure, which is in presence of 1 molar H plus ion solution, and these 2 electrodes are connected through salt bridge. So double vertical line indicate they are connected through salt bridge. So remember the word lone. Left hand electrode is anode, right hand electrode is cathode. So what is the reaction at anode? Zn gives Zn2 plus 2 electron. So there is a loss of electron by the zinc electrode, and it taken by the H plus ion from your solution in SHE electrode. So 2H plus accept 2 electron gets converted to hydrogen. So just now we discuss. And how will you calculate the EMF? That is the cell potential is E cell is equal to E0 cathode minus E0 anode. So standard hydrogen electrode potential minus potential of that zinc electrode to be determined. So the EMF of SHE is 0 minus E0 of zinc and it is nothing but minus E0 of Zn. So if we measure the EMF of this cell, it is found to be minus 0.763 volt, which is the EMF of zinc electrode, or it is a standard reduction potential of zinc electrode. So in this way we can use SHE to determine the potential of unknown cell potential. Now next is, there are some difficulties in setting the hydrogen electrode, that is SHE. First is, it is difficult to obtain pure and dry hydrogen gas. You can't obtain pure and dry hydrogen gas very easily. The second is, the pressure of hydrogen gas cannot be maintained at exactly 1 atm throughout the measurement, because the hydrogen gas get passed into that H plus ion solution, and third one is, it is difficult to maintain the hydrogen ion, that is H plus ion concentration at 1 atmospheric pressure in your electrolyte solution. The reason behind this is, due to the bubbling of hydrogen gas into the solution, evaporation of water may take place, and this results into the changing the concentration of your H plus ion solution. So that's why it is difficult to maintain the concentration of H plus ion solution to 1 molar. Okay. Then next is the types of galvanic cell. So there are two types of galvanic cell. First one is primary galvanic cell, whose potential is known but they cannot be recharged. So all are familiar with the dry cell that is used in our torch, then various electronic instruments such as a remote, car remote or TV remote. So that is a dry cell. Once we use the dry cell, it cannot be recharged. So these cells are called as primary galvanic cell. Then there are some another galvanic cells which are known as secondary galvanic cells. But these cells can be recharged. So once we use that cell, they get discharged, and by supplying the external voltage which is slightly greater than your EMF of your cell, then they can be recharged, the reaction can be reversed. So these cells are called as secondary galvanic cell. Example is Nickel-Cadmium cell, NiCAD cell, Mercury cell, lead storage battery. So today we will discuss NiCAD cell and Mercury cell in detail. Let us discuss first cell, Nickel-Cadmium NiCad NiCAD cell, and they can be recharged. Okay. So here in this cell, anode is cadmium metal, while cathode is nickel oxide NiO2 supported on nickel. The electrolyte used is basic KOH solution. What is the reaction at anode? We know that LOAN, anodic oxidation. So oxidation takes place. So cadmium solid plus 2OH minus aqueous hydroxide ion from KOH solution gets converted into, this cadmium loses 2 electron and it gets converted into CD2 plus. So CD2 plus combined with 2OH minus ion, and it will produce CdOH twice in solid state. So CD gets converted to CD plus 2 electron. So this is loss of electron oxidation reaction. At cathode, there is a gain of electron, that is reduction reaction. So the NiO2, Ni is 4 plus. In NiO2 they accept 2 electron and gets converted to Ni2 plus ion. That Ni2 plus combined with 2OH 1 minus ion and it will produce NiOH twice solid. Okay, so in NiOH twice, Ni is 2 plus. So Ni4 plus gets converted to Ni2 plus by gain of 2 electron. And the 2OH minus from this 2H2 combined with Ni and 2OH minus remains as it is. Okay, so if we observe this reaction, it looks like very difficult, but if you remember in this way, then it is very easy. Cd gets converted to Cd2 plus by loss of 2 electron, and Ni4 plus gain 2 electron get converted to Ni2 plus. Overall is this reaction. But to prepare the compound, we require 2OH minus ion from KHARGE. So that is only the extra part. But main reaction is this one. So here gain of 2 electron gets converted to NiOH twice, and it is a reduction reaction. So combination of these two is the overall cell reaction. So Cd solid plus NiO2 solid plus 2H2O liquid. The 2 electron get cancelled, 2OH get cancelled. On right hand side, CdOH twice solid plus NiOH twice solid. So this is the overall reaction. So if you observe this overall cell reaction, no gaseous product formed during this discharge. This is the discharge reaction of nickel-cadmium cell, and only solid products are formed that adhere to the electrode and are recovered by charging process, which is opposite to this. So CdOH twice solid plus NiOH twice solid gives Cd solid plus NiO2 solid plus 2H2O liquid. So again we get your Cd and NiO2 when we carried out the charging of this cell. Then the cell potential produced is 1.4 volt, which is better than your dry cell. Then what is the uses of this cell? It can be used in electronic watches, calculators, photographic equipments. So this is the nickel cadmium cell. Now next cell is mercury battery. Again it can be recharged. So it is secondary galvanic cell. So let us see the detail about this. So here anode is zinc mercury amalgam, while cathode is the paste of mercury oxide and carbon. Here electrolyte is alkaline paste of potassium hydroxide and zinc oxide. Now let us see the reaction at the respective electrode. Again remember word lone. At anode, oxidation reaction takes place. ZnHg, that is the amalgam of zinc with mercury, plus 2OH minus from your electrolyte aqueous solution. So here Zn is 0 in metallic form, get converted to Zn2 plus by loss of these 2 electron that combine with O2 minus ion, and it will produce zinc oxide. Okay, and that 2OH minus gets converted to H2O by loss of this O2 minus ion. Okay, so O2 minus ion from this 2OH minus combined with zinc 2 plus ion, and it will produce ZnO, and remaining 1 O minus, O2 minus and 2H plus to produce H2O. So the overall reaction is Zn0 gets converted to Zn2 plus by loss of 2 electrons, so oxidation reaction. At cathode, reduction half reaction takes place. So HgO, in that HgO, Hg is 2 plus, that gains this 2 electron which comes from anode, and they get converted to Hg liquid. So Hg2 plus 2 electron gives Hg0 in liquid state. So this is the gain of electron reduction reaction. This H2O liquid gets converted to 2OH minus by gaining O2 minus ion, which is reversed to these previous changes. Okay. Now combination of these two is nothing but overall cell reaction. ZnHg plus HgO, 2H minus get cancelled, H2O get cancelled, 2 electron get cancelled. So this is the overall cell reaction. So it is very simple if we remember in this manner. Zn gets converted to Zn2 plus by loss of 2 electron. Hg2 plus gains 2 electron, get converted to Hg liquid. This is the overall reaction. So you must know the correct charges. Now it does not involve any ion in solution whose concentration changes during the discharge. So here amalgam, HgO is in solid state, ZnO is also solid state, and mercury in liquid state. So there is no ion whose concentration get changed. Therefore this cell provide a constant cell potential which is equal to 1.35 volt. Okay. Then what is the uses of this cell? In cameras, watches, hearing aids, and heart pacemakers. Okay, so this is about the uses of this cell. Then next one is the electrochemical series, or it is also known as electromotive series, or it is shortly denoted as EMF series. So what is EMF series? The arrangement of electrodes with electrode half reaction in order of decreasing their standard potential. That series is called as EMF series or electrochemical series. So there are some points or conventions. So first one is the half reaction are written as reduction reaction, and it is in forward direction, and along with that half reaction or reduction reaction, the E0 value, which is the standard reduction potential, is mentioned. Then on left hand side oxidizing agents are placed, while on right hand side of the series reducing agents are placed. Then at the center there is a standard hydrogen electrode is placed whose potential is 0.0 volt. Below to SHE in the series, the electrode whose SRP value is negative, and it goes on increasing as we go down, while above to the SHE the positive value of that standard reduction potential goes on increasing as we go away from the middle part of that SHE to the top. Then higher or more positive E0 value indicate greater the tendency to reduce, means undergo reduction, while lower or more negative E0 or SRP, means standard reduction potential value, indicates greater is the tendency to oxidize. Okay, now let us see the EMF series. So here at the center, this H plus in presence of hydrogen at the platinum plate. What is the reaction? 2H plus 2 electron gives H2 gas, and the value is 0.00 volt. Okay, and all these reactions are all these half reactions are reduction reaction, because in these reactions electrons are gained, so it is a reduction reaction. Okay, then on left hand side these are the oxidizing agent, and if we go in upward direction, the tendency or the strength of that oxidizing agent goes on increasing, while on right hand side of this series reducing agents are placed, and if we move downward direction, the strength which acts as a reducing agent goes on increasing. Okay, then here standard aqueous electrode potential at 298 Kelvin is mentioned in this electrochemical series. Then all the ions are at 1 molar concentration in water, and all gases are at 1 atmospheric pressure. So if you observe here the detail about this, let us see the application, and you can easily understood how these electrodes are arranged with the help of their standard reduction potential or SRP value. So let us see the application of this SHE with electrochemical series. So first application is relative strength of oxidizing agent. So larger positive E0, that is standard reduction potential, have greater tendency to reduce. Reduce means gain of electron or acceptance of electron. The spaces in the top left side of the half reaction are strong oxidizing agent. Okay, and strength of oxidizing agent decreases from top to bottom. Okay, example is Ag1 plus. So the species which are placed at the top side, they are good oxidizing agent. So if you observe the MF series, at the top fluorine is present, and whose standard reduction potential is plus 2.87, which is the highest one, and we know that fluorine is the strongest oxidizing agent. So non-metals are generally good oxidizing agent. So here fluorine, then chlorine, then bromine, then iodine, they are placed at the top side, and they have positive SRP value. They undergo reduction itself, and they oxidize other substances. Okay, so they are good oxidizing agent, and they are above to the SHE. This is the SHE line 0.0. So I think all of understood. Then second application is relative strength of reducing agent. So larger negative E0 value have no tendency to reduce, that is accept the electron, but they have greater tendency to oxidize, means they loses electron. Okay, so reducing agent loses electron, oxidizing agent gains electron. The spaces in the bottom right hand side of the half reaction are strong reducing agent, and the strength of reducing agent increases from top to the bottom. So let us again observe the AMF series. So as we move downward direction, the strength which acts as a reducing agent goes on increasing, and we know that generally metals are good reducing agent. Okay, so Li1 plus accept electron and gives Li. So, and they reduces other substance. So Li gets converted to Li1 plus 1 electron. So they have tendency to oxidize itself, but they reduces other substance. So if you observe lithium, potassium, sodium, they are the metallic form and they are good reducing agent. They itself undergo oxidation and they reduces other substances. So their SRP value is negative. So we will observe here. So metals, lithium, potassium, magnesium, sodium, they are good reducing agent. They itself undergo oxidation and they reduces other substance, but non-metal, fluorine, chlorine, bromine, non-metals, they have tendency to undergo reduction itself and they oxidize other substance. That's why they are good oxidizing agent. And if you observe, so I think all of you understood. Example is magnesium. Okay, so I am taking this Ag1 plus and Mg. We'll see in the next application. The next application is spontaneity of redox reaction. So if the EMF of the cell is positive, reaction is spontaneous. If EMF is negative or E0 cell is negative, then reaction is not spontaneous, it is non-spontaneous. Let us see example. So one metal which acts as a reducing agent, it's the magnesium. So magnesium solid undergo oxidation to Mg2 plus aqueous plus 2 electron, and this oxidation takes place at anode. So EMF is minus 2.37. You can observe the value in EMF series. The Ag1 plus ion, which acts as a oxidizing agent, it undergo reduction. So Ag1 plus accept 1 electron, 2Ag plus accept 2 electron gets converted to 2Ag solid. So the E0 cathode is 0.8 volt. Then how will you calculate? First we will see the oral cell reaction. So oral cell reaction is Mg plus 2Ag plus aqueous gives Mg2 plus aqueous plus 2Ag. And what is the oral cell reaction? E cathode minus E anode. 0.8 minus 2.37. So answer is plus 3.70. Okay. So if you observe here, magnesium reduces the Ag1 plus, while Ag1 plus oxidizes the magnesium, and the EMF of the cell is positive. That's why reaction is spontaneous. Thus we can say that Ag plus ion can oxidize metallic magnesium, and this cell can work and it acts as a electrochemical cell. If we reverse the cell, means if we change these two electrodes, means here magnesium acts as an anode and Ag plus acts as a cathode. So if we reverse the cell, means Ag plus acts as a anode and Mg acts as a cathode, then cell cannot work because in that case E0 cell is negative. So Ag plus ion can oxidize the metallic magnesium, but magnesium ion cannot oxidize the Ag plus ion. Okay. So for that purpose, one rule is there, and it is called as diagonal rule. An oxidizing agent can oxidize any reducing agent that appears below in the EMF series. So if you observe Ag plus ion oxidize the magnesium because magnesium is placed in the below part of that EMF series than the Ag plus ion. So you can check the EMF series. Those elements which are placed below, they can be oxidized by those elements which are placed at the top. Okay, so this is about the application of electrochemical cell. Thank you. My YouTube channel is Mukesh KHARGE. If you like this video, you can share and subscribe. In next video, we are to discuss the numerical which is asked in board exam, which is based on this topic.